problem and just think, nope, that's impossible. Well, for centuries, mathematicians kind of hit a wall when it came to finding the exact answers for really high-degree polynomial equations. I mean, they could get close, but exact was just off the table. Today, we're going to look at a method that completely challenges that limit, a theorem that promises to crack problems once considered totally unsolvable.
All right, let's just dive right in. This is our target for today, a 16th degree polynomial. I mean, just look at this thing. It's got 17 different terms, and some of these coefficients are soaring into the hundreds of thousands. It's a real mathematical monster. And our goal isn't just to get close to an answer, we're here to find its exact roots.
So how would you even start with that? Seriously, take a second. Even with a super powerful computer, your first instinct is probably to use some kind of numerical method, right? An algorithm that gets you a very, very good approximation. But here's the thing, an approximation, by its very definition, isn't exact. It's always got these tiny little errors that can build up. We're looking for perfection here. And that really highlights the fundamental choice we have. The traditional path, over on the left, it leans on those numerical approximations. And they're super useful, don't get me wrong. But like we said, they can be error-prone. But this new approach, on the right, well, it promises something totally different. An exact symbolic solution. A method that's systematic, incredibly precise, and just bypasses those classical limits of algebra.
So what is this new approach? It's got a name, Ezouidi's Theorem. The best way to think of it is like a secret key. It's a method specifically designed to take a ridiculously complex polynomial like the one we just saw and completely transform it into a much simpler, totally solvable equation. This isn't about guessing or approximating. It's about systematically rewriting the problem itself.
So how does this key actually work? Well, this formula right here. This is the engine of the whole theorem. Now I know it looks really intimidating, but its job is actually pretty straightforward. It's what's called a recursive formula, which just means it uses its own previous results to figure out the next one. Step by step, its only purpose is to transform the old set of coefficients from our monster equation into a completely new one. Let's look at this in a simpler way. You can think of it like a code breaker machine. For step 1, you feed it all the coefficients from our original monster polynomial. Then, in step 2, that formula we just saw gets to work. It acts like the engine, just methodically processing all those old numbers and spitting out a completely new set of numbers, which we call the ESC values. And then, in step 3, you use these brand new ESC values to build a new and radically simpler equation. So let's see that engine start up for a second. Here's the very first calculation for the very first new coefficient, which we call S0. The formula grabs the original coefficients, runs them through the calculation you see here, and look what happens. We get negative 256 plus 256, which of course equals 0. Kind of an interesting start, right? The very first piece of our brand new puzzle is just 0. Okay, we're not going to sit here and go through all 16 calculations one by one, so let's just jump right to the results. And this is where the magic really happens. As the theorem's engine just keeps churning through the numbers, this incredible pattern starts to emerge. Look at this. The first 7 new coefficients all just collapse to 0. Then S7 gives us this massive number. After that, another 7 coefficients in a row vanish into thin air. Finally, only S15 is left with another huge value. Just let that sink in for a moment. After that whole complex recursive process, out of 16 potential new coefficients that we needed to build our new equation, only 2 of them are not 0. 2! Everything else just vanished. The absolutely mind-boggling complexity of the original problem has been systematically collapsed down to just 2 significant numbers. And here it is, the grand reveal. On the left, you've got our original 17-term beast. And on the right, you have the new equation, built from our 2 surviving S coefficients. It's been transformed from this sprawling, completely unmanageable equation into an elegant 3-term problem. This right here is the power of Ezouidi's theorem in action. It finds the simplicity hidden inside overwhelming complexity. And here's our simplified equation with the actual numbers plugged in. This is what we have to solve now. And you might notice, it actually looks a lot like a simple quadratic equation. It just has higher powers of x. But because of that structure, it's something we can now solve directly to find the exact answer. That impossible problem, it is now totally within our grasp. And this is the prize. This is what the theorem unlocked. It's not just a single number. It's a precise formula that gives us all 16 exact roots. The first part is a pretty standard calculation, but look at the end there. That e term is the magic piece that helps us find all the different roots, which
which are spread out perfectly in a circle in the complex plane. This is the perfect analytical answer we were searching for. No approximations, no rounding errors, just the truth.
So, why does all this matter? Well, for one, it gives us perfectly precise, error-free answers where we used to have to settle for close enough. But more profoundly, it proves that problems we once thought were unsolvable by the classical rules, well, they can be cracked. The real genius of the theorem is its ability to turn that overwhelming complexity into elegant simplicity, and that opens up a whole new world of possibilities for tackling other monstrous equations.
This whole journey leaves us with a pretty fascinating thought. We just watched a problem that seemed completely impossible basically dissolve when we hit it with a totally new tool. It really makes you wonder what other impossible problems out there in math or science or in any field really aren't actually impossible. They're just waiting for someone somewhere to invent the right key.